Okay, I guess we are recording. Let me just share my screen. Hey, so can you see my screen and hear me fine? Hello? Okay, good enough. Okay. So yeah, welcome to week 3 live session of your course Introduction to Machine Learning. I'm Raj and I'm a PhD student in IIC. So today's agenda is we'll talk a bit about PSD and PD matrices, and then LDA in Sklearn, and then we'll do like a problem of assignment in case you have any. Otherwise, we'll skip that part. All right. And as usual, this session will be recorded, and the live streaming is right now going on, and whatever is written here will be made available to you in the PDF format. All right. So first things first. Can you guys define for me what is a PSD matrix? What does a PSD matrix mean? Anyone? Okay. So should I assume that you don't know or you don't want to tell? All right. So PSD matrix basically is a matrix which whose quadratic form is like this. That is, let's say I have a matrix A which belongs to R m cross n. That is basically it's a matrix of size m in m rows n columns. If x transpose ax is greater than 0 for all x belonging to n cross n, it's a square matrix, n cross n, for all x belonging to r power n minus 0 or PSD, so it's going to be greater than or equal to 0, right, for all x for all vectors in Rn, right? So that is your PSD matrix. Okay, so this A matrix need not be symmetric, by the way. Okay, A need not be symmetric. All right, PD matrix is basically any matrix which is n cross n and such that A transpose Ax is greater than 0 for all x belonging to r power n minus 0, right? Because for 0 it is trivial. For 0, any matrix you multiply in this format will always be 0, right? So other than 0, any x you take, this value should be more than 0. That is called PD matrix. PD basically is positive definite and positive semi-definite matrix, right? Now we'll do something like, seeing the quadratic form for a general 2 cross 2 matrix. So let's say A is 2 cross 2 matrix like this, A, B, C and D, right? And X is, for example, X1 and X2. If I want to, so what is X transpose AX, right? In this case, so X transpose AX would basically be right. So anyone want to tell me what this finally comes down to? This matrix multiplication. Can you guys see the screen? So what does this correspond to? This becomes ax1 plus cx2, and this becomes bx1 plus dx2 into x1 x2, right? And then this becomes ax1 squared plus b plus c x1 x2 plus dx2 squared. All right. So this is the general form of for a 2 cross 2 matrix, the quadratic form, right? X transpose AX. So from this we can actually build out, what some examples of 2 cross 2 PSD matrices and PD matrices would be, right? So PSD matrix example, if you want to generate, what this means is that this quantity has to always be greater than or equal to 0, right? So if I set something like a equal to 1, d equal to 1, and b plus c equal to, let's say, 2, this would correspond to this x transpose ax would become x1 plus x2 the whole square, right? Which is always greater than or equal to 0. Right? So in this way you can actually construct some examples for your PSD matrix and PD matrices. So for in case of PD matrix, what we could do is we could do something more, so something more from this, right? So I could say that so PD matrices, right? So we could do something like, for example, a equal to 2 and d equal to 2 and b plus c also equal to 2, right? What would this correspond to? This would correspond to x1 plus x2 the whole square, right? Plus x1 squared plus x2 squared, right? Which is greater than 0 for all x vector belonging to r power n minus 0, right? Because what will happen here is that your so here it's possible that it will become 0, right? Because I can always choose x1 and x2 as to be the sum to be 0. Here, even though this is 0, this value will be 0 only when x is 0, right? So in such way you can choose some a, b, and c and so on to make sure that you get some sort of a PD matrix or PSD matrix. Some examples of it. Now see, since b plus d has to, in this example, b plus c has to be 2, right? So I can choose b and c in any format. I can choose b as 1 and c as 1, or I can also do b as -3 and c as 5. Okay, so all this is fine. So basically I can have negative numbers in my matrix also. All right, so don't let your imagination stop here, right? So you can put any real number, right? The idea is that the quadratic form should be greater than 0. We're not saying that every element in the matrix has to be greater than 0, right? And even then, for example, sometimes it may not be PSD, PAD, because the idea is that this form, when you get this form, has to be more than 0 for all x in a PD and should be greater than or equal to 0 for all x in PSD. Is this idea clear? Any doubts here? No? All right, we'll move forward. Yeah. The next, so I had a couple of methods I wanted to discuss about PSD and PD matrices. So let's take this question: is the matrix of this form C transpose C, is this PSD or not? Okay. Any ideas as to what is the answer and how would you go about proving it? Hello? Any idea? If you wanted to prove something like this, what would be your approach? Anyone want to take a try? All right. So the question is, so is matrix of this form PSD or not? So to prove PSD, what we need to do is we just need to look at the quadratic form. So let's say I have a vector x in R power n, and let's say I will choose that, okay, so C transpose C is a matrix in R power n cross n. Okay. So what I'll do is I'll say, okay, x transpose cx. I need to look at this particular, matrix, this particular product. So this I can edit as cx transpose times cx, right? And this is cx norm squared. I hope everybody understands what is a norm here. Anyone who doesn't understand what is a norm of a vector? No? Okay. So, hello? Okay. So this quantity basically is the norm of this particular vector cx, and we know that norms are generally greater than or equal to 0, right? So hence, a matrix of this form C transpose C is always going to be a PSD matrix. Okay, this answer is therefore yes, right? It's always PSD. Okay.
Sir, is there any property is there for PSD expect it is greater than 0?
Which is what you're coming here. So so greater than 0 means basically we're asking, is it PD or not, right? Is it positive definite? So now the question is, what makes C transpose C PD, right? See, very trivially, any PD matrix is a PSD matrix. We want to see the other way around. What could make this particular matrix a PD matrix, right? A positive definite matrix. So any ideas how you will start this question, and where is the difference coming from? So the issue is this, right? So in the previous thing that we saw, it turns out to be the quadratic form turns out to be cx squared, right, for all x belonging to R power n, right? So if it has to be PD, this quantity has to be strictly greater than 0 for all x, right? This is, yeah, so this is what we got previously. So if it has to be PD, cx norm squared has to be greater than 0 for all x belonging to R power n minus the 0 vector, right? So what you're saying is, so norm being greater than 0 means you can just basically say that cx norm squared, so you can just say this has to be greater than 0, right? Okay. Now the point is, I can I say, so under what conditions, right, will this vector cx be non-zero, right? For a norm to be 0, the vector has to be 0, right? So in a way we are saying that this basically implies that cx is non-zero for all x in R power n minus 0. See, for the 0 vector, it is very trivial, right? C into any 0 vector, any matrix into 0 vector will be 0. What we want is for every n, not for every x in the real space, in the real vector space, this has to be non-zero. Okay. Now, how many of you know the idea of rank and rank basically? What is rank? No idea.
No, sir.
Okay. So rank is basically the number of independent columns of a matrix. Okay. So so basically, if let's say a matrix, in our case let's say C itself, for example, it belongs to R power m cross n. Okay, so what this means is it has m rows and n columns. We're trying to ask how many of these columns are actually independent, right? Linearly independent, right? So what is a linear independent? Basically that I cannot express any given any column as a linear combination of other columns in this matrix C. Okay, so if let's say rank is equal to the minimum of m comma n, if the rank of C is this one, then I can say that all columns are independent. All columns are linearly independent. Okay, if the rank is strictly less than m minimum of m comma n, then there is some linear dependence. Okay, and to find that out, you will do like Gauss elimination method and stuff like that to understand which columns can be expressed as a linear combination, and you'll go from there. So the relation between, so here, so basically the idea is that if C is not full rank, right, that is, full rank means if the rank is less than, strictly less than minimum of m comma n. Okay, what that means is there are linearly dependent columns, right? And if there are linear dependent columns, what that means is I can always find, so there exists a vector x, okay, which belongs to r power n minus 0, okay, such that Cx will be the 0 vector. Okay, now I'll just go ahead and give an example so that it becomes a bit simpler to understand. So let's say, okay, so let's say, for example, I have a matrix, 3 cross 3 matrix. Let's say it's 1 2 3 2 4 6 and 3 6 and 10. Now if you see here very clearly, columns 1 and 2 are linearly dependent, right? Because I can always write column 2 as 2 into column 1. Okay, so in a way what I'm saying is I'm saying that 2 times column 1 minus column 2 of this matrix will be equal to 0. So let's say, for example, this matrix is A, for example. So if I multiply this A, if I multiply this A with a vector x, where x is, for example, 2 minus 1 and 0. Okay.
Hello, sir.
Yeah.
So maybe people are waiting in the lobby.
Lobby? No, I don't see actually. No, so there are no people waiting in the lobby actually. Yeah. Yeah, and see, I cannot see the chat. Okay, so if you have anything, just unmute and tell it. Yeah. All right. So if you were to, for example, compute this product a into x, where x is 2 minus 1 and 0, you will get the vector 0, right? So hence what happened is, so you found a vector x such that this ax is equal to 0 and this x is not 0, right? So hence, if C is not full rank, what this implies is that C transpose C will be PSD and not PD, right? Because on PD we have a very strict condition, right? We're saying that if it has to be PD, it has to be greater than 0 for all x which are not in this which is not 0 but belongs to the vector space. All right, so this is the idea. And now I just want to motivate one more thing here. So let's say I have a matrix A, which is, let's say this is the columns of matrix A. Sorry. A2 and so on up till AN, right? So this is a M cross N matrix. And let's say if I multiply it with a vector X, which is, for example, X1 up to Xn, right? Will be N cross 1 vector. The product AX, see, you can find this out in multiple different ways, okay? One of the ways that helps you understand this whole process is that you're taking basically a linear combination of the columns of A, okay, and the weight of each column is defined by this X, okay? So I can write this as basically x1 times A1 plus x2 times A2 plus xn times A, okay? That is sigma I equal to 1 to n xi ai, right? And see, understand the point here that these x1, x2, xn are just scalars, right? x1, x2 until xn are just scalars. So I'm just multiplying a scalar with a vector because a1 is a column vector of is one column of this matrix A, right? This view is important because then what happens is then you can motivate and find out things like these, right? So when I know that 2 times column 1 minus column 2 is equal to 0, I can take 2 times, I can multiply this matrix A with this vector which is 2 minus 1 0. What this means is I'm taking 2 times the column 1 minus the 1 time the column 2 and 0 times the column 3. And I know it will be equal to 0 because of this particular relation, right? And hence you will get this and this you can try to verify it once. Okay, so this is the idea. Okay, so matrix and vector multiplications can be looked at in multiple different ways. There is a geometric interpretation behind this, and one obviously the other thing is you can look at it as a matrix multiplication where this is a matrix, this is a matrix, and you do all your going row by row and everything. That's the usual way of doing matrix multiplication sort of an approach, right? And this is in some way a very like a linear combination of columns sort of approach of thinking about it, right? All right, is this clear? Any doubts? Okay, we'll go to this one. So the next question is like, are the eigenvalues of a PSD matrix non-negative or positive and so on? So if you see here, let's say I have a PSD matrix A. What that means is x transpose AX is greater than or equal to 0 with respective conditions on X, right? So for example, if I have a the what do you call say the eigenvector is, let's say for example, y with an eigenvalue lambda, right? What I can always do is I can multiply y transpose AY lambda y transpose y. This simple. Now see, this quantity is greater than or equal to 0. this is the norm of y squared. So this will also be greater than or equal to 0, which means lambda is basically a ratio of positive quantities, right? Positive quantities. Therefore, lambdas are generally greater than or equal to 0. Yeah. So not positive, actually, I should say is non-negative quantities, right? Because here we are saying that this can be 0 is what we are saying, right? Now, eigenvalues of PD matrix are positive or not. For example, same I can do here. X transpose AX is greater than 0 compulsorily. So I can, if I do this, I get again Y transpose AY is lambda times Y transpose Y. Now this is strictly greater than 0. This will also be strictly greater than 0 because in eigenvector definition, the idea is that you want to look at non-trivial eigen vectors, right? So which is that you say that okay, Y is a non-zero vector. So now, so basically then lambda becomes a ratio of strictly positive quantities, right? So it is lambda is greater than 0. So this is important to understand. PSD matrices will always have non-negative eigenvalues and PD matrices will always have positive eigenvalues. Okay. All right. Okay. This is a simple question in some sense. So let's say if A has eigenvalue small a, what is the eigenvalue of A plus Ki? So for example, if A has eigenvalue A, from the eigenvalue definition, I can always write A into X is small a into X, right? What is the eigenvalue of A plus Ki? So they're asking what is this, right? If I were to get this in terms of X. So I can always write this AX plus KX. From here I get small ax plus kx, and this becomes a plus k into x, right? So the eigenvalue of a plus ki will be small a plus k. Now these things are very in some sense powerful, because if you have the idea of one matrix, I can generate the eigenvalues and vectors of these sort of matrices from that particular matrix, right? Instead of trying to compute everything again. All right. So this is the eigen value, right? So if you see here, the eigenvector has remained unchanged. So this is the eigenvalue corresponding to the same eigenvector. Okay, that's the idea. All right. Then we have, so next question is if I have a non-invertible matrix, right? This implies that there is at least one zero eigenvalue and vice versa, right? So if you want to go from here to here, let's say, okay, what that means, it means that so if something is non-invertible, let's say A is non-invertible, okay, this means that the rank of A is, or I can say A is not full rank, right? And we already dealt with how to understand this A is not equal to full rank thing, right? So we said that there will exist a vector X such that AX is 0. Okay, there exists a vector AX. Yeah, which so X is 0, right? So therefore, now see this, I can write it as AX equal to 0 times X, right? So therefore 0 is eigenvalue of this particular vector, of this particular matrix, right? So there's at least one 0 eigenvalue. Okay, now if you have a 0 eigenvalue, what does it mean that it is non-invertible, right? That's the question. And similar thought process you can use. So you can say that if AX equal to 0 times X, that means AX equal to 0, right? So there should be, that means this X basically is telling you that I can take some linear combination of A's and get 0, right? This means that a linear combination of columns of A will be 0. This means that I can express one of those columns, right? One of those columns as a linear combination of the other columns, and therefore I have linear dependence. And this basically means the rank is, what is it? It's not full rank. Okay, not full rank, which basically means it is not invertible. All right, cool. Okay, we're running short on time. Okay, fine. So idea is that so can we connect all of this to ridge regression basically. So the idea is that if you remember, your linear regression had a solution of this form, right? So you had x transpose x into x transpose y in a linear regression setting. Inverse, sorry. In ridge regression, what happened is you said x transpose x plus lambda I whole inverse x transpose y. This is ridge. All right. So now we already saw in the first few things of this particular lecture that x transpose x is basically a PSD matrix, right? So it's possible that the eigenvalue of this will be 0, right? And in case it is 0, and why it will be 0, it's basically if x is not full rank, right? If x is not full rank. So if the eigenvalue is 0 for this particular matrix, we also saw that if I have a matrix of this format, right, the eigenvalue for this particular matrix will just be eigenvalues of this plus lambda, right? So eigenvalues of x transpose x plus lambda. And we have said that I will always set lambda greater than 0, strictly greater than 0. So what happens is this makes sure that you have only non-zero eigenvalues. Of this new matrix will always have non-zero eigenvalues, right? Which means that you will get a invertible matrix from this one, what we discussed just now, right? So it has no zero eigenvalues, which means it becomes invertible. All right. So this is the idea on ridge regression. There's a bonus question, so I'll just put it out here. You can see in the PDF version and see what these things represent. All right, so we'll go to the programming part of this session. Basic so in LDA, what are the basic assumptions we are making? They're basically twofold. One is that the class conditional densities are Gaussian, right? So what is this probability of x given some class y is equal to, let's say, k is a Gaussian is Gaussian. And second thing is that all of these Gaussians, that is across all the classes, your covariance is the same, right? Same for all class conditional densities, right? These are two assumptions of LDA. And for so the general form for trying to understand this logarithm of probability of belonging to a class, so y equal to k given x is basically some weight vector times x plus some constant, right? So let's say w1 w0, but these are for each class, right? So this is in some sense the intercept in their high dimensional space, and this is the coefficient, or basically the linear term that is so and hence you can see that this becomes a linear function x, and hence you get the term linear discriminant analysis, right? Yeah. So now week 3, so if you see here, I'm just going to give you an understanding of what how to use LDA in Sklearn. All right, so we can take a simple example of iris dataset. Okay. Yeah. So in the iris dataset, if you see, I have 150 data points, okay, and 4 features for the particular flower in some sense, and you have and we are trying to deal with 3 flowers here, 3 types of flowers: Setosa, Versicolor, and Virginia. Mm, um, yeah. This is your train test split. That is, you're taking part of the data in train, part of the data in test. I'm also stratifying. If you don't know what this means, we can discuss in the next class. But yeah, so I try to figure out like why this would make sense in these settings, right? Okay. So this is the function which basically takes which has your method for LDA in Sklearn. You fit that on the train, and you can visualize what are the coefficients that were learned. So if you see here, it's a 3 cross 4 matrix. So 3 because you have 3 classes, right? So for each class you define the coefficients for your linear plane, right? And then so that is your 3 comma 4 shape, and the intercept is basically going to be like a 3-dimensional intercept, right? Because you're defining one intercept per class. And then you get your score here. Here score basically means the accuracy on the test set, 93.3%, which is a good. And then you can predict on this particular X test to see what actually the predictions are made on the X test. And you can try it on one sample. So for example, I'm looking at the 0th sample here, first sample here, and so then the question is, how do you get the probabilities, right? So there's a predict proba method in Sklearn that will give you the probability of the sample belonging to all the 3 classes. So if you see here, 4.9 into e power minus 19, so which is 10 power minus 19, very low probability of belonging to class 0, very high probability for belonging to class 1, which is hence it is predicted it to be 1, and again medium probability for belonging to class 2. Okay, and how do you get it is because you have this logarithm, right? You have this log so you have this log p of y equal to k given x. So if you want to get the probabilities, you will just take the you'll take this over e, right? You will do this e power something. That would be just the probability in a very naive sense, so unnormalized sense. So you have to normalize it. So what you will do is you will take that sum over all the classes, right? Which is what we're doing here, right? So we're taking the we're getting the multiplication stuff here, right? You're multiplying the coefficients and the sample and adding the intercept. You got some values. You'll take the exponential of these and then divide by the sum of all exponentials to get the probability distribution. As you can see, these things basically match. So okay, running out of time again. So the idea is that you can run this for simpler settings also, right? And try to understand how to get these probabilities out from this system. Okay, so now a couple of you told that we want to look at real world data. So we have this something called as ABIDEII dataset, which is basically trying to work on, can we detect autism in patients and subjects as such, right? Are they autistic or not, and can we understand that from brain scans? So these guys, they basically get some structural MRI information, okay, and they use something called as free surfer software package to basically generate some anatomical features, right? So let me just go forward. So if you see here, this is, for example, let's say a human brain, and we can change we can get parts of the human brain using different methods for getting the parts here. So here there's something called as the multimodal parcellation paper by Glasser et al. Okay. So this particular paper shows that we can divide the brain into 180 regions per hemisphere. There is 360 in total, right? And each region is basically a volume in space, right? It's a 3-dimensional stuff in space, right? So what we can do is we can actually find out what is the surface area, the volume, the thickness, and there's something called as local gyrification index, right? So for each of those parts of the brain, right? So yeah, so we basically get that information, and we can now look at, whether a particular person has uh, autism or not, based upon the structural MRI that you have taken, right? And doing some pre-processed variables, which is your free surfer variables, right? So if you see here, for example, okay, this has to be uploaded. Okay, it's not loading up now. Okay, so I'll just go ahead with here whatever we have here. So as you can see, for example, ABIDEII, the data frame, basically you can see has things like the subject ID, the age of the subject, what is the gender, what is the group that it belongs to. Group is the one that basically means, so if one means that the person is autistic, and two means that it is not autistic, also called as control sort of a variables. And then you have all of these data that we obtain from free server. So if you see here, so first thing is, like, you can check the, how many things do we have for each class that we have. So we have two classes, and we have 53% of the data points belong to zeroth class, and the one class number one we have 46%. So it's a balanced data set, so which is a good thing. And then you have, what are the free surfer variables that you get. So you have, so these are the areas of the brain in some sense, right? So your V1 is basically your visual cortex, which is at the back of your brain, the primary visual cortex. And then you have V2, V3. We have FEF, which is a area called as frontal eye field, which controls the eye movements for your eye, and so on. And then we have something called as the side on which hemisphere does this area belong to, which is left and right hemispheres. And then you have these four variables that you get: the area, surface area, the volume, and the LGI and the cortical thickness. So what you can do is, you can basically look at, how a subset of variables does it help you predict whether the person is autistic or not, right? So you can see here, these are all your variables belonging to the volume component. And you can see, for example, we have 1004 subjects, data points, and 360 variables in total, right? Because we have 360 areas of the brain, uh, right? And then you can just divide the data set into train and test. You can do your same sort of analysis here, and then you can see that we are getting a score about 61%, right? So which is not that good, but it tells you that there can be some relation between the structural information in your brain, and uh, whether you can or you are autistic or not, right? So these sort of things basically help scientists to understand, can we solve issues like autism through medicines or not. So because if there's a structural component associated with them, then we need to think about even more robust sort of approaches to solve for this sort of issues, right? So that's about what I had planned for today. We're anyway running out of time, so I'll just say that, I was hoping to do some assignment problem, but we won't be able to do right now. But if you have anything, just put on the discussion forum, right? And any questions as such currently? No? Okay, then we'll stop the recording here. We'll stop meeting here, right? And see you guys next week. All right. Thank you. Thank you for being here.